Hello and welcome to this video on diode laser rate equations. In this video we're going to investigate what happens when you feed current into a p-n junction and eventually cause light amplification by stimulated emission of radiation. The derivation I'll be presenting here is based on the one found in this book called Elements of Photonics, which I highly recommend for a deep dive into the details of modern laser and optics technology. The system we'll be looking at today is a p-n junction, like so, with a certain depletion volume, and we'll see what happens when we feed current into this. I want to stress that the model I'll be presenting here is a very simplified description of how the band structures of a semiconductor laser actually arise in the first place and how they truly behave. So I encourage you to check out some of the links in the description for more details on this. But essentially we're going to assume that we have a valence band down here and a conduction band up here separated by some energy difference, like so. And when we feed current into the system, we're essentially stripping electrons out of the valence band and dumping them into the conduction band like so. Here they're basically going to stay for a time duration, tau n, before they spontaneously recombine with holes in the valence band, producing photons in the process. Now, there's a number of processes taking place in this system that we have to analyze separately. First of all, there's the process of spontaneous loss. So if you imagine that we have mirrors on both sides of this cavity, the photons produced can sort of bounce back and forth until they interact with an impurity or some defect in the cavity that causes the photon to be scattered away off the axis like so. This allows us to write down an expression for the probability that a photon is still inside of the cavity after a certain time duration t. This depends both on the scattering parameter alpha as well as the speed of light within the cavity, which of course depends on its refractive index. In addition to this, we also have loss from the mirrors. In a sort of typical or conventional gas laser, for example, you'd have actual mirrors on both sides of the cavity. But for a semiconductor laser, it's usually sufficient to rely on the Fresnel refraction from the transition between the gain medium and the air outside. It turns out that if the gain medium has a typical refractive index of around 3.5, then the reflection of the ends here is only 0.3, which is actually kind of low. But fortunately, the gain inside of a semiconductor laser is so high that this actually isn't a big problem after all. Anyway, the point is that we can write down a combined expression for the probability that a photon is still inside of the cavity after a certain duration. And doing a little bit of simple algebra that combines both the effect of spontaneous loss and mirror loss, we see that the scattering rate of photons out of the cavity is given by this formula here. And if we take its inverse, we get the average lifetime of a photon within the cavity like so. An important fact that we'll need for further calculations is that the ratio of the photon lifetime to the opposite electron lifetime is around 1 to 1,000, with the lifetime of a photon being around 1 picosecond, and the lifetime in the opposite here being around 1 nanosecond. So we're going to use this later for some approximation, so keep it in mind. Another process that can take place is the process of stimulated absorption. The idea is that just as we can recombine an electron with a hole down here and produce a photon, the opposite process can also take place, where a photon interacts with an electron in the valence band and promotes it back up into the conduction band, which should happen right about now, I think. Yes, there we go. This allows us to write down a differential equation that describes the rate of change of the number of charges in the conduction band as a function of both the present number of charges up here and the number of photons inside the cavity. Note that with this expression, if n is very low, then this overall becomes a positive expression, and this implies that photons will tend to promote electrons up into the conduction band here. But on the other hand, if n is very large, we see that it's negative, meaning that electrons are basically forced back down into the valence band. That's the process known as stimulated emission. Essentially, if the conduction band is highly populated, then the recombination of one electron with one hole that produces a photon can then trigger all of the other electrons to also recombine with the holes, producing even more photons in the process. Let's just see that one more time. So we get a recombination, produce a photon, that then forces all of the other electrons to recombine and producing more and more photons. That's basically stimulated emission, which is in the laser acronym. Since there's one photon produced for every electron that recombines, we can write down these two coupled differential equations here that describe the rate of change of the photons within the cavity and the number of charges in the conduction band. Note here that the n alpha is sort of a theoretical number of charges in the conduction band, where if we have perfectly refractive mirrors and no loss and also no additional of extra electrons from the current, then that will sort of balance these two effects out. All in all, we can write down these two coupled differential equations for the rate of change of the number of charges in the conduction band, and the rate of change for the number of photons within the cavity. Note that this term here is the number of charges added by the current that we are supplying. This is the stimulated absorption part, and this is the spontaneous loss due to recombination. Note also that when I write S and N, I'm actually talking about the number densities, so the number of charges per unit volume, like so, and the number of photons per unit volume as well. Furthermore, note that the S here is the number of coherent photons, and essentially the reason here is that whenever a photon triggers the recombination thanks to stimulated emission, it produces an identical photon, and this sort of cascading effect will tend to cause sort of one type of photon to dominate within the cavity. But there is also some production of amplified spontaneous emission, which we're going to ignore in this duration. Our plan now is to first analyze these two coupled differential equations below the so-called lacing threshold, and then subsequently above the lacing threshold. Next, we'll take a look at how the activation time depends on the bias current that we're selecting. And finally, we'll take a look at some relaxation oscillations and what happens when you modulate the current that you're sending into the laser diode. So first of all, if we're below the so-called lacing threshold, it means that the number of coherent photons is very small, so we can neglect any term that contains S. Next, if we're in a steady state, it means that all derivatives must be equal to 0. So this allows us to solve for some concentration of charges here below the lacing threshold. And just isolating, we find this expression here, which clearly depends linearly on the current as well as the upper state lifetime. And it kind of makes sense that before lacing starts, then the number of charges we get in the steady state in the conduction band should depend both on the current we're feeding in and how long the charges stay in the conduction band. So graphing it out, we see that we get this linear increase, like so. But now we have to analyze what happens above the lacing threshold. If we're above the lacing threshold, we can no longer assume that the number of photons is equal to 0. But if we're in a steady state, we can still assume that these derivatives are equal to 0, giving us some steady state number of charges here and some steady state number of photons being inside the cavity. Cancelling out the steady state number of photons, it's very easy to solve for the steady state number of charges above the lacing threshold. And interesting, this is equal to a constant, which we'll just label as n threshold, like so. By equalizing this expression with this one, it's easy to find that the threshold current is around this magnitude right here. And I think for a typical semiconductor laser, this is going to be on the scale of like maybe 10 milliamps or something along those lines. We can also note this expression here, which is valid when we're above the current threshold. And it's just something that's worthwhile to note for further derivations. So we can of course also isolate an expression for the steady state number of photons above the lacing threshold. And I'm going to go through a bit of algebra here and not spend too much time on it, but I hope you can follow along just using these steps I'm presenting here. But the final expression here we get is simply that the steady state number of photons is linearly dependent on the supplied current above the current threshold. So essentially the picture we get is that as we increase the current, the number of charges builds up, and when we hit the threshold current, it just flattens out. And that's when we get an increasing number of steady state photons coming out like so. So maybe an interesting question here is, well, why do we get this sort of flat response when we feed more and more current in? So why don't we get any kind of increase in the total steady state number of charges? And basically the reason is that as you keep feeding more charges in when we are above the current threshold, those charges just get instantly converted into more photons and don't really have a chance or any time to build up in the conduction band before being instantly converted into photons. Alright, so that's all well and good, but it's still a very static analysis of the response of this laser diode to the supplied current. So what happens if we keep the current at 0 and then suddenly switch it on? How long is it actually going to take for us to build up enough charges in the conduction band for lacing to begin? To determine this, we can solve a time-dependent version of the previous equation fairly easily, thankfully, by just dividing through like so and integrating on both sides. And doing a little bit of simple integration, we find that the delay time between activating the current and lacing commencing is given by this formula right here. If we graph it out, we see that it is a decreasing function of this ratio here. And in principle, if you pick a set current that's just above the threshold, then it should take infinitely long for lacing to start. But if you pick any value that's just even slightly above, you get something that's pretty reasonable, around like 1 nanosecond, or the upper state lifetime, like so. Another way to think about this is that the inverse of this activation time is on the scale of 1 gigahertz. So in some sense, that sort of puts a limit on how quickly you can switch a laser diode on and off simply by activating or deactivating the current. Now, in the old days of optical telecommunication, that was sort of the first order approach to sending signals with a laser diode. That isn't how it's done these days. These days, you're more likely to actually run the diode in continuous wave mode, feeding in a steady current and then pulsing the optical signal externally. But anyway, it's sort of a nice little insight into how the diode responds when you switch the current on and off. We can make this analysis a bit more detailed by picking a sort of bias current that's just below the threshold and then activating the current just beyond that threshold, like so. In that case, of course, we expect the time delay to be smaller. To figure out how the time delay looks in this case, we can simply solve the same equation as before, but now integrating from a bias number of charges all the way up to the threshold number, like so. And rearranging it a little bit, we get this formula here, which very clearly reduces to the previous one for the case of the bias current being equal to 0. So graphing all this out for various values of this bias current, we see that we can actually make it a lot smaller when we choose a bias current close to the threshold. In fact, if we divide through by the baseline case of having 0 bias, we can see that we get an improvement of a factor of 100 if we choose a bias current like 99% of the threshold current. So one small thing to note here is that the amount of amplified spontaneous emission, or noise you can say, is going to be fairly low when this bias is close to 0, but it gets higher when we get closer to the threshold. So essentially, if we were to actually pulse the laser in this way, we would get a lower signal to noise ratio if we operate with a high bias here. But anyway, sort of for modern purposes, it's kind of an obsolete approach to sending signals anyway, but it is nice to know if you're going to do some kind of sophisticated experiment with laser diodes, we have to switch them on and off very quickly. Anyway, so I've also numerically solved the differential equations I showed you earlier, and what we see is that if we set a fixed current, we get a steady buildup of charges in the conduction band like so, and if we let a bit more time pass, we can see that here we hit the expected time delay, and then a little bit later we see that there's a big spike in the number of photons coming out. But interestingly, if we let a bit more time pass, we see that the number of photons actually drops again to a very low amount, and then spikes back up, and then drops and spikes and drops and spikes, and keeps sort of bouncing back and forth, and sort of exponentially decreasing like this. And you also see there's a wiggling in the number of charges in the conduction band. So what happens is a bit more obvious if we plot this on the log scale. We can see there's almost no photons inside the cavity until we hit the time delay, and then the buildup starts to happen here sort of exponentially until it sort of overspikes and scoops up all the additional charges built up in the conduction band. Then there's a sort of interesting wiggling effect where it drops down and then builds back up, like so and so and so until it hits or sort of approaches the steady state number here. I've linked to a Python notebook in the description where I've simulated all of this, and of course you can download it and play around with it if you want. But this sort of recurrent spiking behavior is sort of interesting. So let's try and figure out if there's a way to describe this, or at least understand it with the equations we saw earlier. Essentially, if we start with a small number of charges and a small number of photons, then the equations will basically look like this, where the rate of change for the number of charges is dominated by the supplied current. There's almost no increase in the number of photons. But when the number of charges gets very large, then we have a situation where suddenly it's going to decrease itself, because you can see that both of these terms will become very negative. But if n is very large, then s will still be quite positive. That's why we saw this sort of big spike in the photon number as the number of charges was dropping down. However, if n then becomes small again, it once again becomes dominated by the number of charges we're feeding in thanks to the current, while the number of photons will become very negative, because now n is very small, so this overall becomes a negative expression. That's why we saw this big dip in the number of photons coming out. But then now both of them are small, so the whole process just sort of repeats and cycles. And the point is that we basically expect some kind of cyclical exchange between the number of charges and number of photons, especially if there's any kind of change to the current as we activate it or maybe modulate it. In more detail, we can see that if we extend the timescale a bit, we get these big spikes in the number of photons in the beginning, but it sort of exponentially decays down and turns into something that looks a bit more like a sine wave down here, which is something we're going to see in a bit more detail in just a moment. We can also do something interesting in doing a sort of a phase space plot. So we can see that this green line just follows the number of charges and number of photons over time, starting for a very low value here, and just increasing, and then spiking up with a big number of photons and dropping back down, and just sort of cycling around until we hit both the threshold number of charges and the steady state number of photons. It's a bit easier to see if we zoom all the way in here to this location. We can see we get this sort of cycling behavior between the number of charges and number of photons that sort of spirals into a steady state value around here. But anyway, let's see if we can actually prove that we get this sort of behavior just analytically. So we're going to assume that the steady state number of photons being inside the cavity has some additional small variation s sitting on top of it. And then the same thing for the number of charges with the threshold here, and then some variation on top. And the same thing for the current. If we plug these expressions into the previous formulas, we can get this formula here for that would be the variation in the steady state number of photons. And then expanding out this parenthesis and noting that n times s is going to be a very small term, so we can drop it out. It gives us this formula like so. Then using a previous expression that we derived earlier, it's possible to eliminate this term with this one, and this one with this one, and essentially arrive at this formula here for the rate of change in the variation in the number of steady state photons. Because it depends both on the variation in the number of charges as well as the steady state number of photons like so. Doing the same thing for the charge equation, we can pull some similar tricks here, expand out the parentheses, drop the small term here, and then we can simply rearrange things and also use this formula right here to cancel out these terms with each other and obtain this equation right here. So cleaning this up a little bit, we see that we have now two equations here that still look fairly complicated, but at least this one seems a little bit simpler. To make things even simpler, we can actually take another time derivative on both of them. And the idea here is that we can now take this equation here for the derivative of n and plug it in down here, and this expression for the derivative of s and plug it in here. And this allows us to decouple the two equations. In fact, that's just what I've done here. You can see that this equation now, even though it contains a lot of terms and factors, it only depends on lowercase n here, here, and here. And of course also the derivative of the current, but that's something that's sort of being fed in externally. It's not really coupled to the number of photons directly. We can do the same thing for the second derivative of s here, and using this previous expression here for the rate of change of s and the relation to n, we can also decouple this from the number of charges, or the variation in the number of charges. Finally, we can rearrange things so that all the derivatives on the left-hand side and the source term over here with the current is on the right. So all of this still looks fairly complicated, but if we squint a little bit, we can notice that this is just equivalent mathematically to the equations for driven damped harmonic oscillators, which is something that we're fairly familiar with modeling. Here we've defined these two parameters here that essentially you can think of as some kind of resonance frequency and some kind of dampening parameter. And we're going to look into more of that in just a bit. Now, in the following here, we're going to use some of these expressions I've derived earlier, so I'm just going to remind you of them, so hopefully the following algebra is a little bit more clear. I won't explain the algebra in too much detail, but hopefully you can follow along. First of all, we can think about relaxation oscillations in S. So let's imagine that we've activated the current and then fixed it to some steady value so that there's no variation in the supplied current at all. In that case, the differential equation for S looks like this, and we can now ask, well, how long does it take for these variations in the photon number to actually die out? In order to figure that out, we can write down this equation here, or we can rather assume that the behavior of these variations in the photon number is some kind of sinusoidal function. Note that we're allowing for omega to be complex, so it has both a dampening behavior and an oscillation behavior. If we substitute this into the equation over here, it's fairly easy to show that the possible solutions for omega are given by this formula here. And plugging this back in, we see that there is indeed a dampening factor here, according to gamma over 2, and some kind of oscillation factor here that depends both on omega r, as well as the ratio of gamma to omega r like this. So we can actually express the attenuation rate in terms of the supplied current, as it turns out. If we do a bit of algebra here and replace some of these terms, we eventually find that gamma is going to depend on the difference between the supplied current and the threshold current. In fact, if we also define this parameter I alpha, like so, we find that the damping parameter is given by this formula. Now, the insight here is basically that as we increase the supplied current, this dampening constant becomes larger. So if you supply a high current, you expect the oscillations to die out more quickly and for the steady state to be reached much faster. Also note that since this depends on 1 over the upper state lifetime, it's going to be on the scale of like 1 gigahertz or so. taking a look at the relaxation oscillation frequency, that's basically given by this whole formula right here. But you might be wondering, well, how quickly is the actual oscillation frequency to this omega r parameter we defined earlier? In other words, how big is this ratio of gamma to omega r actually? To figure this out, we can expand the expression for omega r like so, and use some of our previous tricks here to also rewrite that in terms of the supplied current. So if we do that, we essentially find that omega r is given by this formula here, and we see that we get much faster oscillations in the photon number if we supply a higher current. Note also that since both tau s and tau n appear in this expression, we can plug in their sort of typical values and find that this is on the scale of like 10 gigahertz or something like that. So since we found that gamma was around 1 gigahertz, then this ratio is going to be quite small, especially when we square it. So 1 minus a very small number is basically equal to 1. So it turns out that the oscillation frequency here is basically equal to this omega r frequency. So not exactly equal, but very close to each other. In other words, we now figured out what happens when we just make the current completely fixed, and then we see how the oscillations die out over time. But what happens if we're actually actively modulating the current that we're sending in, like switching it on and off, or maybe just having a sinusoidal variation of the current? Like, what an impact does that actually have on the variation in the number of photons coming out? To analyze this, we can imagine that the variation of the current is also a sinusoidal function, and the same thing for the output number of photons. Note that in this case, omega m is assumed to be a real parameter, because we don't apply any dampening to the current that we're sending in. We're just imagining that's a perfectly sinusoidal function. So with this assumption, we can feed these two expressions into the previous formula for the number of photon variations. And essentially we find this amplitude right here to be given by this expression. Oh yeah, and by the way, we can of course write that omega r squared is equal to this, just to keep it a bit more simple. So if we rearrange this slightly further by rationalizing the denominator, we can put all the complex behavior into an exponential up here, where of course phi depends on some of these parameters feeding in both omega r and omega m. But it doesn't really matter, because we're only really interested in the amplitude here, not if there's any kind of phase shift relative to the input current. So this exponential part doesn't really matter at the end of the day. Now, if you actually graph this out, we're going to get functions that look a little bit like this. So here you can see the blue curve is for a resonance frequency of 5 gigahertz and a decay parameter of 1 gigahertz, while the orange one is for a 7.5 gigahertz resonance. You notice that it's both shifted to the right, but also has a higher peak right here, indicating that it sort of responds more strongly to current being modulated at this particular frequency. Sort of causes a larger variation in the photon number coming out. We also see that if we increase the dampening parameter, we get a lower peak and sort of a faster decay towards zero for higher frequencies. Now, a small, initial analysis we can make here is to assume that the modulation frequency is much smaller than the resonance frequency, meaning that it's somewhere over here. And if we approximate a lot of things, we can find that this is basically a sort of parabolic increase for small frequencies like so, and that sort of seems to be pretty accurate. But it's actually even more interesting if we assume that this ratio is very, very, very small, because in that case, we can see that it's a perfectly flat response right here for tiny frequencies. And it's a bit easy to see if we plot this on a double log scale. So what does this sort of flat region actually tell us? Well, it tells us that if we imagine that we have a diode like so, and that we feed a train of electrical pulses into the diode, then as long as the harmonics of these pulses are low compared to the resonance frequency, they're all going to be located in this sort of flat region right here, which means that they all get mapped one-to-one to the optical domain. So whatever pulse train you're sending in here is going to be mapped completely into optical variations, as long as you're in the low frequency regime, like so. But this of course changes if you send in a pulse train with higher harmonics that are closer to these resonances here, because in that case you might get a distorted pulse coming out, since some of these harmonics will be basically amplified by the diode responding much more strongly to those variations. Another thing to notice here is that if you increase the pulsing frequency of the electrical current much more, then you get into this regime here where there's a steep drop off in the response, meaning that if you modulate the current extremely quickly, you basically get no photon variation coming out on the other end here. In principle, you could also see this as a sort of beneficial effect, in the sense that if you, let's say, want a very large variation in the photon number coming out, then making that variation happen at a frequency that matches the resonance of the diode can actually give you sort of more photon variation for the same current variation coming in. Not really sure why you would want to do that, but it is possible. So there is another, or final, sort of important observation we can make here, and it's a little bit subtle, so I will explain it in detail. When we feed current into any kind of system, it's typical that we report the current in terms of amps, which essentially is a measure of the number of charges passing into the conductor per second. And if we have, let's say, 100 charges coming in, it's very easy to imagine that we just have 100 charges every single second. But the reality is that any kind of current always consists of a very large number of independently arriving electrons. And in nature, whenever you have any kind of behavior where many independent events take place at some average rate, the actual number you see within any given time window is going to follow a so-called Poisson distribution, like so. This distribution has the property that if there's some kind of average arrival rate within a time window, lambda, then the standard deviation of that arrival will be the square root of that average rate. And furthermore, if you have a very large average rate, the distribution will basically look Gaussian. And you can see that even for an arrival rate of 10 per second or per unit time, we get something very close to a bell curve, like here. The reason this is interesting is that if we actually plot out the true number of electrons arriving per second, if you have 100 on average, we see that there is indeed some average rate here, but there's some variation sitting on top of it that sort of is random from time to time. And if we take the Fourier transform of this, we see that it's as if we have a very large number of current frequencies being present simultaneously that all have some kind of average amplitude, but which have, well, I guess for a particular evaluation, it's all going to be sort of random amplitudes, but on average, for very many iterations, it's going to be just basically flat and present at all frequencies. So the point I'm trying to make here is that even if we don't intend to deliberately modulate the current that we're sending in, the statistical nature of current, it consisting of many charges arriving independently, means that it's as if we also have a very large number of sort of random frequencies being sent in that all have the same amplitude and completely flat from low frequencies all the way to high ones. And the point of this is that even if we want to keep the current completely fixed, we're always going to get a little bit of variation on the photon number coming out, just thanks to this is the statistical nature of the current. Now, this isn't necessarily the only thing causing random variation of the current, but it is one that will always be present. The point here is that we can measure the variation of the photon number coming out in the time domain, and then if we take the Fourier transform and compute the absolute square, we get what's called the relative intensity noise in the frequency domain, like so. Now, of course, this can be measured experimentally or simulated numerically as I've done here, but thanks to our previous expression, we can also take these current amplitudes that come from the random variation in the electron number and then feed it into our previous expression for the theoretical photon amplitude. And the idea here is that whether we do it experimentally or theoretically, we essentially get the same sort of curve coming out like so. You can see that here we have the red curve from my numerical simulations and the pink curve from the theoretical expression here. And you see they agree quite well and peak at 7.16 gigahertz, the same like so. Okay, so why is it interesting that we've modeled this relative intensity noise theoretically? Well, it's interesting because in a lot of experiments, it's important that the variation in the photon number doesn't exceed a certain limit. For example, if you have a very basic setup here with a laser diode and a photodiode that has some finite measurement time and some maximum frequency sensitivity, then you basically imagine that the power you measure over time is going to look like some kind of randomly varying signal like so. And if we don't want that to exceed a certain, let's say, a peak value or certain RMS value, it's nice to know how the design of the laser diode could be changed to make sure that this variation doesn't exceed the specifications. And now, thanks to our knowledge of the response of the photodiode to the supplied current, we can essentially model this theoretical response or the theoretical distribution of noise, and then integrate that from the lower frequency here determined by the measurement time to the upper frequency determined by the response of the photodiode's bandwidth. And just doing this simple integral here will essentially tell us the RMS variation we expect from this laser diode. Then of course we can change the design if it doesn't fit the specifications. Let's give it a tick mark if it's within the limits. So I hope you found this video on diode laser rate equations interesting. Feel free to check out some of my other videos over here and stay tuned for more. Bye bye.